Howdy, folks. Welcome to a wonderful, reasonably wonderful Tuesday afternoon here in November. Just a couple quick things to cover today. I am currently without my hydrogen, which is fine. Hydrogen went in for repair as part of the Houdini program. See Houdini. It's great. Nice little sweatshirt and everything like that. One of the things that happened was the fingerprint reader stopped working at one point along the way. They identified it as a bad batch. We got it all rectified, and actually I will have my replacement showing up here tomorrow. That is what a warranty will get you. Actually, great customer service. Great call-outs just call-outs to Nicole, Tony, Jim, Jammin, all the guys and gals over at Red Edgar. For everything that they've done. It's an incredible experience with them. Not the primary focus of what tonight's going to be about. So two things tonight. Well, we'll cover two things. We'll see how well we can make this happen. I'll try to keep it short as well, but some of the stuff is interesting to me. So first thing was the announcement yesterday, I believe it was. Yeah, I'm going to go with yesterday, about Cascade Lake AP, or Advanced Processor. So what Intel has done, for those of you who are not aware, Xeon SPs, so Xeon Scalable Processors, okay? What they do is they basically scale in cores from, I think, 8 cores. Don't quote me on that. You can go to arc.intel.com, look up the scaling of that. Anyway, they have scaled processors, right? So silver, gold, or bronze, I think. Bronze, silver, gold, platinum. Platinum being the high end, whatever. What they've done is basically, in the absence of I'll be very gentle here, a workable 10 nanometer program, for these processors, and we can go into what those are in a later conversation. Part of the way that they're trying to stay competitive is they have now taken 2 of those Xeon SP processors, platinum ones, and they have co-joined them together into what's called an advanced processor, an AP processor. The co-joining basically uses something called multi-chip module, right? Or multi-chip module, MCM. It's an easy way of doing it. So what you have is, essentially, if this is the module, ignore the writing on it. If this is the module, then what you're doing is you're taking 2, this core A, set of cores, stick them on a module, back to back, and you're doing something like this, right? Real basic. What's not so basic is what's required in order to get those cores talking together. What's required to get those cores into the same socket. Now remember, sockets are generally pins or pads, right? And processors interface with those pins and pads to some extent. And so that's where your electrical, your communication, all your signaling goes through. One of those landed grid arrays, or land grid array, or LGA sockets, is significant in size. I mean, you're talking about something that's roughly the size of a business card, right? Putting 2 of those processors together in the same socket means you have to double the power delivery, you have to double the communication protocols or whatever, double the memory channels, et cetera, et cetera. So a lot of tracing work needs to be redone. So what's happening is you're going to have a new socket for that. So I'm going to use this as a pitch point to talk about the next little situation. So we put these 2 modules together on the same substrate. It's great. We now increase the socket area. We try to commoditize and find the common power delivery vehicles between the 2. We have to stitch those cores together so they can talk to each other. So some sort of communication protocol. Intel's case, that's called UPI. Figure out how those things are going to communicate together, figure out the amount of those links in between all those cores. So Intel runs what we're calling an HCC, or high core count module on either side. That's what it's made up of. So being able to get out of, in this particular case, it's a 48 thread, or it's a 48 core or 96 thread device. So each one of those has 24 cores. So those 24 cores like to talk together. These 24 cores like to talk together. They're their own domains, if you will. So getting all 24 of those to cross-talk and access each other's resources, it becomes a challenge, right? So you got to solve that electrically. You got to solve that via communication protocols, and you got to solve everything else that goes in that system. Now, if you're going to create multiple sockets within a system with that, it's going to become a journey, not a fun one. So that's going to require some engineering work. It's going to require a new socket, like we're saying. So an infrastructure change is happening with that. Now, there's some upsides and some downsides. The upside is it is a cheap and easy way. I say this. It's a cheap and easy way to take dies that you've already put on they're coming off a wafer, take them, bin them, put them together on a single substrate, put them on a module, and ship them, right? You now get two for the price of one, so to speak. Your costs are going to be ridiculous, though, because your cost would be less than developing those discretely and packaging them discretely. However, your overall aggregate cost is going to be more for that particular CPU now with that one on that MCM than it would be if it was just a single device. So that's something there. Also, because you're increasing the density of power, the density of compute, and the density of this communication things, outside of the retooling that you have to do in order to make sure memory channels and everything else are done, you're also having to adjust the thermals of the system in order so that it doesn't blow the whole fucking thing out, which is kind of a problem. You're suddenly going from, in each of those particular cases, you're going from a TDP or a thermal dissipation of around 205 watts to something that can easily approach 400 something watts within a given socket. That's a lot of power dissipation, especially when your nearest competitor is running 180 to 205. Keep that in mind as well. So that causes a not so insignificant approach to things. What do? You lower the core clocks. You decrease some of the extraneous power feeds. You make sure that base and boost clocks were done within reason, and so on and so forth, right? So there's some fuckery you can do. You have to do in order to make things work the right way. All right. So that's the Intel Cascade Lake AP, or Intel Scalable Processor AP. Sampling right now, I believe, and they said they're shipping in first half of 2019. Why that's important? AMD today announced Rome, which is Zen 2, if you will, or EPYC in next generation EPYC, right? Zen 2. So stepping back to original Zen already did multi-chip modules. Actually, when it was launched, it would look like a set of 4 dice arranged on a substrate, and it was shipped as a processor. They already took the hit on the credit card size thing, and people used to comment, "That's such a massive processor." Yeah, it's not small. I will give you that much. Intel did the exact same thing. Whatever, we'll let that slide. But what AMD did was actually pretty tactical. Now, the way they set it up originally is each one of these things was a self-contained processing unit, right? 8 cores, or 4 cores, 4 cores. L1, L2, L3 cache. Contained some PCI Express links, and contained what they call Infinity Fabric links. And so they were able to glue 4 of these things together in their EPYC package, right? So EPYC, the 7601, for example, which was 4 of these together on a single substrate, 32 cores, 64 threads. Remember, AMD is now doing symmetric multi-threading, or hyper-threading as Intel likes to call it. It was all well and good, but that design enabled something to happen with Zen 2, where they moved to a chiplet model. Now, chiplets are a little bit different, and here's where it gets really fucking exciting, right? Instead of having to design a very monolithic and integrated type core, right? CPU, L1, L2, L3 cache, or CPU cores, cache, any kind of I/O feeds like PCI Express PHYs, any kind of signaling protocols, Infinity Fabric, memory channel controllers, so on and so forth. What you do with a chiplet is you get it down to the barest amount of resource that you need. So in this case, Zen 2 is basically a chiplet that is cores in cache and Infinity Fabric. You have to have a communication protocol to the outside world. What that Infinity Fabric stuff does, and we'll use the prongs as the example of that allows us to plug into what AMD has announced as an I/O hub. Now, an I/O hub has the receiving sockets for the Infinity Fabric, contains some memory controllers, so on and so forth. These chiplets then become the unit or the organic unit of growth for how you want to scale that MCM or that processor, right? So now you can take 8 cores, plug in, take another 8, plug in, take another 8, plug in, all the way up to 64 cores now on their kind of flagship or Halo part. That's 64 raw cores, and that's 128 threads in a single processor using the same footprint that they already had. Do the math there. That's pretty impressive. Now, Intel's doing the same thing, but they're taking AMD's old formula, slapping things together, making them glued, but they're only getting 96 threads. And they're doing it in a power envelope that's almost double. Well, by the time they're done, let's say it's not almost double. They're probably going to be a little bit less than that, but it's going to be a very, very powerful thing. So that's one of the innovations that came out of that. Obviously, shrink to 7 nanometer versus Intel's 10 or 14 nanometer or 14 nanometer plus. There's some die size advantages. There's some silicon advantages there as well. But I cannot emphasize enough, chiplets are the way things are going to be going. That allows me to plug resources in. So if I look down the road, I'm a betting man, things like PCI Gen 4, which, by the way, Rome will have, or Epic 2 will have. If I look at C6, if I look at Gen Z, if I look at any of these kind of communication protocols that allow for systems or discrete units to be expanded upon, remember, there is no memory controller on these chiplets. Think about that for a second. No memory controller. So what if I had a whole bunch of chiplets on a substrate that I plugged into one aspect of a system, and then over on the other side of the system, I had a whole bunch of memory that was plugged in, and then in the middle I have an arbitration hub. Technically what you're describing is something that Gen Z promises to do. Interesting, right? There's a method to the madness here. So all this stuff is being in the public domain. There's no NDA information that I am containing or that I have contained in here. But think about it. Prognosticate. The whole idea is to start moving these things, into the various pools which make them most efficient. This also starts to work down true composability. Now, everybody is probably chewed over composable infrastructures more and more. It's a huge fucking marketing term. If you know where I work, we have a product that is composable infrastructure. And the cool part about composable infrastructure is the idea behind it is I can take anything, mash it up together, use it, and when I'm done, I dissolve it into its discrete components, right? So chiplets, chip, memory, storage, networking, however I need to do, system I/O, bandwidth, storage, whatever. I can take all that, use it for what it is, and then when I'm done with it, it goes back into its discrete units. Now, that allows me then to leverage out as I need to go. I compose what I need, right? I can create what I need. When I'm done, I get rid of it, right? It's a fantastic concept in theory. Praxis is a little bit more difficult because why? We haven't really focused around the chiplet concept of stuff. Yeah, it's been done. We've demonstrated these kind of processes and possibilities, right? But the ability to kind of look at things from that and say, hey, I need this CPU component here. All right, cool, done. I need this memory component here, done. I need to stitch it together somehow. Infinity Fabric or Gen Z or C6, right? More like Gen Z. C6 being a different story. Yeah, you start to couple all this stuff together, and now I can build these systems, I can build these units of growth, or I can build these kind of organic components into something that resembles a monster of a machine if I need it to be, or very, very simple, right? And I take that through an entire AMD, processor line. This stuff gets fucking fantastic. The second best part of this whole idea, as I mentioned tangentially, the PCI Gen 4. So Zen 2 will feature Gen 4. PCI Express. This is some almost immediate doubling of bandwidth per socket, per slot, right? The other cool thing that does is that allows you to start using, specifically in AI, machine learning, deep neural networks, convolution, inference training, spiking neurals, that kind of stuff. It allows you to get really good bandwidth because what's the biggest limiter right now, can be one of the biggest limiters right now in terms of feeding those type of devices, general purpose GPUs or accelerators like FPGAs. It's getting data to and from, right? You need a lot. There's the potential for that cache and carry. You need that across. These are part of the reason why NVLink becomes so important, right, to NVIDIA's story. So it allows that load and store operation and the coherency between the devices that are in the system. So not only does Rome provide that level of kind of communication, it also does some very interesting stuff when coupled to something like the MI60, MI50, and MI25, which are the Radeon Instinct cards for machine learning, AI, inferencing, that kind of stuff. It allows this kind of organic bandwidth growth up to 100 megabytes or 100 gigabytes per second. we're gonna use the fuckery math, which is basically quote both bidirectional, 50 gig one way, 50 gig the other way. We'll quote that as a whole, right? 100 gigabytes per second. So creating that kind of closed loop topology across 4 of these cards gets about 400 gigs of aggregate bandwidth across all these things. Marketing math, whatever. And then allows you to bring it back into the system, and you have the ability to assuage a lot of that, or at least get that flow control going through PCI Gen 4. Very, very important, right? This is just high-level stuff. Obviously, the devil's always in the details with both the Intel side and the AMD side and how this practically works out. But these are the things that are super exciting and things that are definitely worth paying attention to. So that's all from a Tuesday night. Promise some updates tomorrow when I get my hydrogen back. Looking forward to that. I'm going to be taking some more pictures. There's been some massive software releases, so definitely check that out. And yeah, hope you guys have a great night and enjoy the ride. And make sure you voted. Well, at least here in America. So, all right. Adieu.